now what we want to do is actually decompose this total efficiency, eta total, and we can actually decompose it into two different efficiencies, the multiplication of two different efficiencies. But first, let's look at the physics of these two. Since you have the engine and it accelerates the air, so you have some kinetic energy that is left behind in the atmosphere from the engine, and of course it is being dissipated into heat eventually. Furthermore, the air which is leaving the engine has very high temperature, and also there is some heat left behind in the atmosphere. This increase in kinetic energy of the flow per second is what we call jet power, and it is the kinetic energy rate behind the engine minus the kinetic energy rate in front of the engine. We are showing this jet power with P J in here in this slide. So if we look back at the total efficiency equation, the thing you saw it in here, you can also express it as the power available divided by this thermal power Q, and then here you do a little trick in here, and in order to separate different energy losses and to get more let's say understanding into the physics behind this process, you just use Pj jet power, just multiply it and divide it by the jet power. So the total efficiency, when you do it like this, can then be written as a propulsive efficiency eta J multiplied with thermal efficiency eta thermal, eta Th. Now let's have a closer look at the propulsive efficiency, and the eta J is defined as the power available divided by the jet power. So these two, power available, jet power. Now if you write these terms, then the power available, of course, is the thrust times airspeed, you remember, and the jet power, as we say, is the half of m dot Vj squared minus this is the rate of kinetic energy behind the engine minus a half m dot times the airspeed squared, v squared. So this is the speed, the v squared is the speed of the aircraft. But of course, we know that thrust can also be written as mass m dot times Vj minus v, you remember. So then of course you still have to multiply it with the airspeed, because you have the thrust times airspeed. So what you see in the denominator is that what we can take half of m dot to the left, and then multiply it with Vj squared minus v squared, And after some um, let's say manipulation, you will get to this formula. This formula is 2 times v over v jet plus v. And this is interesting because um uh, when you can remove this v from denominator and numerator as well, you only got this formula, 2 over 1 plus vj over v. So this greatly simplifies our equation because we only have vj and v in here, and our propulsive efficiency is only the propulsive efficiency is only the function of the jet velocity and the flight velocity. Uh, so the propulsive efficiency, we said that it's purely depends on the ratio of the jet velocity and the flight velocity, right? This is Vj over V or V0. So if you can draw a graph of this equation with actually propulsive efficiency is on the y-axis, and the ratio of jet velocity to the flight velocity is on the x-axis. You can observe that as the ratio increases, propulsive efficiency decreases. Okay, and in addition, I should mention that the jet velocity is always larger than the v velocity, v0 velocity, the air speed of the vehicle, and uh, therefore propulsive efficiency is always smaller than 1 or smaller than 100%. And this is very easy to understand because in order to create some thrust, you have to accelerate air, and physically, if you think, you will leave some kinetic energy in the atmosphere behind the vehicle. So that is considered as the loss of this system. So once the aircraft is passed, you just lost this amount of kinetic energy, and this equation gives us an opportunity to um, make an interesting observation through a very simple example calculation. So what we are thinking, uh, maybe uh, to consider this example. mm, so I meant that this propulsive efficiency is always less than 1 or less than 100% because you have left some kinetic energy in the atmosphere. So it will be considered as the loss of this system. So and now we have derived all the essential equations concerning the thrust, the power, the efficiency, and now we have all the materials to go back to our original problem, which is to express the thrust force as a function of airspeed in order to simplify the equations of motion. So let's first consider uh, a type of propulsion system which is called the jet engine. So the second case we will consider is the propeller engine. So first let's start with this jet engine. You know, the basic operating principle of the jet engine is actually shown in here. Uh, Incoming air uh, flows into the engine, and it will be compressed, and then some fuel will be injected in the combustion chamber, and the combustion starts, and the air is heated up to a very large amount of temperature, and because it has a very high temperature and pressure, then this air wants to expand, and during the expansion it flows past the turbine, and uh, this turbine is connected to the compressor through a shaft, as you can see in here. So it is also rotating the compressor. After the turbine, um, the air still has lots of energy, and it can expand more through the nozzle that you see in here, and then it will expand it up to the jet velocity and leaves the engine. So the jet velocity mainly depends on the energy that is put into the gas with the fuel and the pressure of the gas inside the engine. Uh, so even though there is some compression of air in front of the engine, when it is not uh, uh, when it has not yet to the engine, uh, but the majority of this compression is achieved inside the compressor part of turbojet engine, and the amount of energy that is put into the gas is limited by the maximum temperature. The maximum temperature is limited by the material of which the combustion chamber and the first stages of turbine are made. So this is a basic principle of actually a jet engine. So now our aim is to find that uh, how this thrust force of jet engine is changing with the air speed. And to do that, if we just have a fixed, uh, let's say, throttle settings, throttle uh, means how much fuel you allow to pass to the jet engine and burn it. So first of all, you have to consider the equation, the thrust equation. So you see it is mass flow rate times the difference of velocity at the jet and the flight velocity. So if you increase the air speed, then mass flow will increase. Okay, when the speed increases, mass flow also increases. But the point is in here that the jet velocity is not really affected uh, actually to a great extent, because the jet velocity mainly depends on the compression ratio. Compression ratio means how much air is compressed inside the compressor. And also this is a function of the throttle setting. So if you fix the throttle setting and you have a fixed compressor, so if the compressor ratio is fixed, then the jet velocity is not very dependent on the flight velocity. So okay, we know that if we fly at higher speeds, maybe the compression in front of the engine will change a bit, but this is just a very small effect compared to the other effects that we have in here. So mass flow increases if you just increase the speed, but the velocity difference decreases actually. So this one increases, this velocity difference decreases, and they can cancel each other. So the jet engine thrust will remain more or less constant as a function of airspeed, when all other variables, such as we said, throttle setting and the altitude the flight is happening, will be kept constant. So in this picture you see the variation of thrust force with flight speed for a real jet engine, and there are three lines as you see. um, the maximum thrust, climb thrust at the climb, and thrust at the cruise. Of course, um, you can select any of these or in the middle of any of these, but you have to select it below this maximum thrust line. But what is important is that if you just check these lines, these are not changing very much as the velocity is increasing. So we can consider that these are fairly flat, and we can show that the thrust indeed remains more or less constant for variable velocity, variable airspeed, like I just explained. And because of this specific behavior, for the current calculations, we can assume that the thrust is constant with airspeed. So you see that this thrust force, the thrust force is this red line is actually a flat line, as it is not changing with the airspeed. So again, remember we did have the calculations for the drag force, and you just remember that the drag force had the quadratic form, quadratic function of velocity. So drag force actually can be represented like this blue line in here. So if you just consider the power available for a jet engine, you remember that the power available is thrust times velocity, right? So if you just want to sketch the power available versus airspeed, then for a jet engine it will be a straight line that is starting from the origin, from zero. And uh, actually we will learn that the power required is also a function of drag, because you require some power to come up with this drag. Okay, so uh, you can say that the power required is also changing like the drag, and actually drag times the velocity will give you the power required. So it will be a not a quadratic function, but it's the cubic function of velocity. We have v squared in drag force, but drag times one velocity more will be v cubed, so v to the power of 3, and this is actually the power required. The function resembles to the power required. Okay, as I said, we can consider a propeller engine as well. So here you see some uh, figure of a propeller. So there is a blade on the propeller, and it is essentially a rotating wing, and it is creating lift and drag because it is a wing. So the part of this lift and drag, which is to the right side, to the which acts forward, or we can say this the part of the lift and drag which is perpendicular to the plane of rotation is making a thrust force, and the part of lift and drag which is in the plane of the rotation, not perpendicular to that, will create some torque for us. So you already know what is torque, and this torque is exerted on this shaft of the propeller, which actually derives the propeller. So actually this torque needs to be overcome by the engine that is connected to the propeller. So the velocity of blade depends on the rotational speed and the forward speed of the aircraft, and these velocities also determine the local angle of attack of a blade section. And together with the geometric angle of the blade, which is indicated by this beta in this figure, these are actually determining the velocities inside the velocities of the propeller. The most important thing is that an increase in flight speed will result in a decrease in angle of attack, and thereby in a change in lift and drag in the propeller. So uh, most modern propellers have a constant rotational speed, and they have variable geometric pitch. So when you change the pitch of the propeller, the angle of attack and therefore the thrust will be controlled. And in each flight condition, the optimum setting can be selected for the propeller. You see some of them in here. So if one wants to draw a diagram with propulsive efficiency as a function of airspeed for fixed settings, it would have the following shape. At one specific flight speed, you're seeing one specific flight speed, the propulsive efficiency will be maximal. Okay, do you see these maximum points? One is here, one is here, one is here. So it happens only at one specific velocity. However, if you draw the same graph for various propeller pitch setting, you can see that the optimum value will be shifted. And because of this, it's possible to select the maximum efficiency at each flight speed by changing the propeller pitch. And if you assume that the engine delivers a constant shaft power, for example, by means of a conventional piston engine, the propulsive efficiency used for evaluation of jet engines can be replaced by the propeller efficiency, which we define as the power available divided by the shaft power. So if the shaft power is constant and efficiency is kept constant by varying blade pitch, the power available will be constant as well. And this is very important result because this means that power available will be independent of flight speed for a given flight altitude and a given throttle settings. So keep this in mind, and this of course is the theoretical behavior because it also implies that at zero velocity thrust will be infinite. But in reality, the thrust and power available of a variable pitch propeller have these following shapes as you see. So the range of flight speed of interest for performance calculations in our studies is in the range where the power available is indeed constant. So you see this is the available power which is constant. So from now on, I will assume that the power available for propeller aircraft is independent of airspeed for a given flight altitude and a given throttle settings. So if we conclude, we have expressed the propulsive force for both pure jet engines and variable pitch propellers as a function of airspeed in order to simplify the equations of motion. And because of the simple form of the thrust and power curves, this allows us to analytically calculate the aircraft performance as we will see in our courses, future courses through aeronautical engineering. Now, you might wonder, but what if an aircraft is equipped with a propulsion system that does not have this simplified behavior? For example, if an aircraft is equipped with a turbofan engine, which can be seen on most commercial aircraft today. So to answer this, if the engine manufacturer provides us the thrust or power variation with airspeed, then we can still do all of these calculations. Sometimes in that particular situation, the calculations will then have to be performed either graphically or numerically, and you cannot solve it again analytically by hand. So this actually concludes the treatment of the behavior of the propulsion system, the thrust force for aircraft performance calculations. So to wrap up, um, it's useful to summarize what we have learned so far by drawing a free body diagram and the kinetic diagram or kinetic diagram. Uh, for some specific aircraft, we are able to derive the uh, equations of motion, mass equations of motion. And as we said, there are two variables in these equations. There are a speed and the flight path angle gamma. And describe these are state variables. Why? Because they describe the state of the aircraft. And after analyzing the aerodynamic forces like lift and drag and the propulsive force, the thrust, we are able to describe all of these forces as a function of airspeed and Thereby, we can make these equations much more simpler. Also, we saw that the aerodynamic drag forces, as a function of airspeed, has this blue curve at left, this shape, quadratic form. The power curve is simply aerodynamic drag multiplied with airspeed. So the power is v to the power of 3 cubic form. And in these graphs, we can also draw the thrust or power available from the engine. And for a pure simplified jet engine, the thrust can be assumed independent of airspeed, and a typical simplified propeller shows that the different we have a different behavior. The propeller with a variable pitch setting can be assumed to have more or less constant power available as a function of airspeed. So the diagrams that you see here are called performance diagrams. And because of this different behavior of jets and propellers, we normally use the force diagram for jet and the power diagram for propeller engines. So you will see in the performance course that these diagrams combined with the equations of motion will allow you to do many aircraft performance calculations. So to summarize what we have learned in aeronautical engineering, we learned about the atmosphere and generating lift force. Also, we introduced some forces which are caused by the lift force, like drag force. So these forces exerted on aircraft are actually studied in the aerodynamics. So this is one part of aeronautical engineering. Also, we had the opportunity to see the structure of aircraft and its materials. So this is another branch of aeronautical engineering. We also studied some preliminary stuff about the propulsion and control and stability, and at last we said that how we connect all of these details in order to uh, study the performance. It goes into the flight mechanics branch of aeronautical engineering. So by this I will finish the aeronautical engineering, the principles of aeronautical engineering for this semester, and I wish you had a good time during this semester with these course materials, and I wish you good luck during your career and during your studies. Thank you very much and have a good day.